Hi, everyone. A little bit of echo. Okay, we're good. Hi, I'm Kat. So technically, I'm the developer advocate for the open source robotics foundation, the people who make ROS, Gazebo, OpenRMF. Technically, I work at Intrinsic, which is a Google X subsidiary based in Mountain View. I'm also on the board of the Open Source Hardware Association. So I really wanted to come talk to you guys really quickly, not so much about ROS, but actually about Gazebo. So like I said, we at the OSRF and the OSRA maintain 5 big open source projects, ROS, Gazebo, OpenRMF, ROS2 control, and the ROS infrastructure that supports it. And what we'd really like to figure out is how to get Scenic integrated with Gazebo. There's 2 ways to do this. One might be through a grant through the Open Source Robotics Alliance. This is a new program that just kicked off 3 weeks ago. So it's a yearly program that could be an option, but we'd actually have to have people propose it and fund it and drive it. And we need to have sort of requests coming in from the community that they'd like to see Scenic integration within Gazebo. The other thing that we could look into perhaps to bring Scenic into Gazebo is perhaps doing a Google Summer of Code project. To make that happen, I would need to find somebody who is a core maintainer for Scenic to work with probably a core maintainer of Gazebo, and we'd need to find a student to make this happen. My understanding of the state of Scenic integration is that Scenic integration exists for Gazebo Classic, which is now end of life. And we do not recommend people use Gazebo Classic any longer. Modern Gazebo, also called Ignition or formerly called Ignition, is on its 10th release. We're actually working on the 10th release right now. And what we'd like to do is figure out how we can bring Scenic integration back into Gazebo. Like I said, to do this, we'd actually both have to find developers on both sides of the aisle, and then we'd also have to find a willing and capable student. And we'd have to probably have this process set up by roughly, I would say, March or April of next year, so we can apply for the Google Summer of Code program. So that's the main process. If you're interested in the sort of projects that we took on this year, they're starting to wrap up. On the right there is actually some recent work with Modern Gazebo to integrate some, I'm not really familiar with sonar. It's some particular kind of sonar simulation inside of Gazebo for subsurface simulation and robotic simulation. But that just wrapped up. That's one of the features we've just added or about to add. Other than that, if you would like to dip your toes into Gazebo maintainership, we're actually pushing right now, starting next Thursday, the final push to get the Gazebo Jetty release out. So every year when we do our Gazebo release process, we sit down with the community, we run through all of our tutorials, the entire Gazebo installation process, and test everything with the new release to make sure everything works, to make sure that all our documentation is up to date and performing correctly. And we need the community's help to do it. And it's a really quick and easy and simple way to get started with Gazebo development if you'd like to understand how the project works. So that's all I have. I think I had 5 minutes, so great. Any questions? Yeah. Oh, so every year when we do a release, right, subsequent, instead of saying Gazebo 9, Gazebo 10, Gazebo 11, they're letters, and those letters turn into architectural words. So Jetty is the J release. Yeah, so every year it's either like some sort of architectural term that we use to, just like Ubuntu, right? Or ROS. Okay. Thank you, everyone.
Okay. So I just wanted to briefly segue the people's two thoughts that Kai here, a student at Berkeley, who has actually been doing some Scenic based integration. So see the beginnings of it. So this is something we want to build on, and so this is also a good topic for the working group session that's following this one.
Again, this kind of coworker, so one of the gazebo form.
Yeah. And so the gazebo interfaces we've had was actually one of the videos shown on the Scenic websites was the Toyota HSR. And then lately our lab has published a multi-agent robot tool that was also using gazebo with the ROS2. So then the further integration is also an alphabet item on our agenda. So sorry, wrong Zoom. All right. My name is Kai. I'm a incoming PhD student at UC Berkeley.
And I'm Martin. I'm a visiting student from KTH in Sweden.
And today we would like to present to you some of our recent implementation of features in support for reinforcement learning and some ongoing efforts in applying it to humanoid robotics. So now everybody here knows Scenic, but I just want to give a quick note on Verify, which is one of the foundation of our tool, with the foundation tools that we base our work on. So as you will learn later this afternoon, Verify is a tool for formal design analysis of AI-enabled systems. It does a series of functions, including falsification, fuzz testing, error table analysis, feature space search, etc. It is a tool that is highly integrated with Scenic. What happens is that the user inside a Scenic program can specify distributions with distributions that Verify will analyze and sample inside a Scenic program. So, for example, on the right side is essentially like a standard Scenic program. In here, we spawn two robots and inside a scenario. And we have some parameters being sampled by Verify. For example, in line 15 and 16, we have the X and Y position of the fetch robot is something that Verify actively sort of monitors and also samples from. And what happens in this process is that Verify will have its own sampler. In this case, we specified it to be a Halton sampler. It samples these sequences at each episode. And then for a lot of those samplers, that at the beginning of the episode, it will essentially consider the history of the past performances of your agent, and then figure out essentially which feature, which distribution that it is responsible for. It is most correlated to the performance of your robots, and then it will figure out essentially where in those regions are most likely to yield a poor performance from your robot. So essentially, it's a sampling-based falsification process as a gross simplification. Now, these, as you also learned, that these distributions that Verify are responsible for is considered to be the semantic feature space on which you perform analysis. And you will learn more about these concepts later in the afternoon. But this is a tool that we base on. So the idea has been that we would like to combine Scenic and Verify for reinforcement learning training of cyber-physical systems. And what happens is that Scenic and Verify, they fit very naturally inside the framework of reinforcement learning. And in fact, previously, back in 2022, Eddie actually led that work, was that we actually our lab has applied the Scenic and Verify into the reinforcement learning training of soccer, in a soccer scenario in the Google Soccer Simulator. But however, it is also our desire to actually apply this to train cyber-physical systems, but also to build a more integrated tool that combines Scenic and Verify for reinforcement learning that is compatible with a lot of your modern reinforcement learning libraries and algorithms. So in this scenario, in this case, Scenic will essentially model the scenario, will describe and generate your episode, and Verify will essentially try to generate sample parameters in such a way that you have episodes that force your agents to perform poorly. So combined, they can offer a compact and interpretable way to generate data that gives some kind of confidence in your case coverage. So what we have been implementing and what we have implemented is this thing called ScenicGym. It is a gymnasium environment that uses Scenic and Verify underneath. It also has corresponding headings and wrappers for your multi-agent trainings. Under the hood, Scenic and Verify will generate sample episodes according to the Scenic program. And then at the end of the episode, you compute a sampler feedback to the Verify sampler. It can be, it is generally computed according to your agent's performance. And a vanilla example can be the total episode reward that is obtained by your agent within the episode. The user can define the feedback upon instantiation. It can be anything you want. The total episode reward is just a vanilla example. Now the function should, as an implementation detail, the function should take in like a Scenic simulation result object as an input. Now the verify samples parameter in general, samples parameter in an adversarial way in order to essentially lower this feedback value. So in the case of your feedback being the total accumulated reward over the episode, verify will just try to generate episodes that are harder for the agent, such that the agent achieves lower and lower reward. So that is the background implementation. And in terms of usage, this just shows you how to use ScenicGym. On the left side is how you instantiate it. Line 29 to 31 is quite your standard gym stuff with your observation and action spaces. 33 to 36, you have Scenic. This is using Scenic programmatically. You specify a Scenic file and compile a scenario from it. And on line 40, you instantiate the ScenicGym environment for your reinforcement learning training. You pass in the scenario. In this case, this training was run in the habitat simulator. So we have instantiated a habitat simulator instance on line 41. And then the only thing that we want to provide that is special is on line 46, the feedback function. In this case, it is the cumulative reward that we have obtained over your episode. And then we instantiate the environment. On the right side, nothing special. It is to show that we are using this with stable baseline 3. So it is compatible with your modern reinforcement learning algorithm libraries.
Right, so now I'm gonna go through an application of ScenicGym and especially to humanoid locomotion. So first some background on common approaches to solve or try to solve humanoid locomotion, and especially locomotion on rough terrain, is by using this kind of curriculum where you have different terrain types and you have different parameters that determine the difficulties of these terrain types. And then you add as input to the policy that you train using reinforcement learning, different points that give the height around the robot. And using this curriculum in combination with the terrain height observations, you can learn fairly well to traverse these different terrain types. So this is like a general overview of the idea of using ScenicGym with locomotion over rough terrain, where you have a Scenic program defining the terrain by defining a distribution over the different parameters for these different terrain types. And then you feed this program into ScenicGym, which samples a scene from that program, and you then train a policy or evaluate a policy on this sampled scene. And you then give feedback back to Verify that can then resample new scenes. This is a very simple example of a program defining different terrain types and the distributions over the parameters defining these terrains. So you can see that we have random uniform terrain here and different distributions over parameters defining these different terrain types. So I'm gonna go through 2 quick examples showing a humanoid being trained on these different terrain types and then evaluated on Scenic sampled terrains. So yeah, here we can see this is a policy trained using an existing environment in Isaac Lab, which is like a reinforcement learning framework on top of the Isaac Sim simulator. And it's learned quite well using this curriculum learning approach to traverse different terrains. And here we have another example where we evaluate it on, or it's the same policy as the baseline, but we evaluate it on Scenic generated terrains. And we can quite easily find examples where it fails, as you can see here. And every time we reset the environment, we sample a new terrain. So in that way, we can quite easily find cases where it fails. And here is another example of another humanoid, which is the humanoid that we have in the lab I'm at in Sweden. And this humanoid is a bit less robust in general than the G1 robot. So you can see that, yeah, here is basically flat terrain, but as soon as it becomes more challenging, it starts to fall. So some challenges is, as you could see before, that robotic systems, especially for legged robots, they're quite fragile. So it's not super difficult to find failure cases. So it might be a good approach to try to focus more on more robust systems, and where it's harder to find cases where it fails. And then something like Verify can be very helpful to find the cases where it fails and it shouldn't fail. And we're also going to use more experiments with adaptive sampling, especially using the reward function as the feedback, and also cross-simulator training with something called Roboverse and MetaSim, which you're working on.
Yeah, so cross-simulator training has been one of the main things that we have been targeting. So towards that effort, first of all, you can use Scenic to train really any simulator that Scenic supports. But another efforts towards cross-simulator training, especially with robotics, is that we are developing an interface to the set of simulator called Roboverse, which is essentially a meta simulator that wraps around a suite of other robotic simulator that supports cross-simulator training. And eventually, the goal is to be able to work towards a simulation to reality transfer, and to have robust humanoid robot locomotion on different kinds of terrains.
Thanks.
Yeah.
So Corina is joining to take questions. Any questions for Kai and Martin?
I guess to your the future work thing you mentioned at the end about adaptive sampling and Verify.
Right.
I don't know if you've thought yet about using that for training as well as for testing, or is that what you had in mind?
So the idea was that, during training, so we want to use adaptive sampling, but during testing, I think the idea was that I think Verify becomes a very good platform for actually more rigorously evaluating reinforcement learning.
Sure.
Right, because what we found is that sometimes, if you have an agent that is more their robustness is not reflected just by the reward function. So sometimes the robustness really does require you to actually run a falsification with verifying Scenic as a better way, a more rigorous way of actually evaluating the performance.
We can talk afterward, because Kay has done some experiments with using Verify for training. We have different samples in Verify for training.
Right.
Thanks.
Thank you.
So sorry, what is the time?
No, I think you're good.
You're ready.
You don't
So
need to unmute there. So you just talk over there. At this
you can
laptop.
come put your laptop here.
Yeah, it looks good.
And then, yeah, you can go ahead.
Okay, thank you.
Next speaker is Corina from CNU and NASI.
Okay, thank you so much for the introduction. So this is a presentation that I created last night because you told me I should give a presentation. So please bear with me. So this is very informal. So actually, I gave a colloquium here in May, I think, and I talked about my current work on the analysis of perception neural networks using vision language models. So I'll tell you quickly what the idea was and then try to explain, what I see the connection with Scenic, and hopefully we can work together. And so in that work, I already explained. So the challenge that we try to address is that we want to reason about, and also possibly automatically verify, semantically meaningful properties of vision neural networks. So there is a semantic gap between high-level properties that can come from requirements, and I'll give some examples, and the inputs to a vision neural network that are raw pixels or video frames. So our idea, which we presented last year at SAIV, small symposium affiliated with CAV, is to use a separate vision language model as a lens that peeks inside the embeddings of a perception module. And this is what I explained last time. So vision language models are similar to foundational models that are trained both on images and text. And they output a similarity score between an image and caption. And our idea is that you can then formulate natural language requirements about the image domain and use that to reason about the images. And we have a construction that also trains a map between the image embedding of a perception module that is shown on the left-hand side and the image embedding of a VLM, for example, CLIP. We have used CLIP in our work. And in this way, we can specify properties, and we define in this paper a specification language about our vision model, and then use, with the help of CLIP, we give semantics to the properties, and then we actually define verification procedures for that. And this is some background. As I said, these are multimodal transformer models, and they are trained on many image caption pairs. So our hope is that, and we use them as oracles, as you know, they are word models. They know a lot about images and their descriptions, and we want to leverage them, as I said, to peek inside the perception module of an autonomous car, for instance. And this is more another quick background. So this kind of, I'm not sure it's relevant here, but just to remind you about my previous work. So these vision language models can be used as zero-shot classifiers. This means that even for domains on which they were not trained specifically, you can use the similarity scores that they compute to build classifiers for free. So for instance, if we have classes truck, cat, dog, bird, and different images representing these classes, we can basically compute the encoding of the image and the encoding of concept cat, which is written in a natural language description, and compute the similarity score, which, for example, for CLIP is cosine similarity, but models use other scores. And then we can say image X is classified as, for example, cat, if all the conditions on the left-hand side hold. And, for us, we want to, so of course, the class itself for an image could be seen as a property, but you can also imagine you can decompose these properties in finer grained properties. For instance, for cat, you can say it has fur, blue eyes, and ears, while for a truck, it is rectangular, metallic, and wheels. And then, similar to the way one can do zero-shot classification, one can also encode properties about these more basic concepts. So, for instance, for an image of that shows a cat, we would expect that the cosine similarity between the encoding of the image and the encoding of concept fur is greater than the encoding. Sorry, I don't know how to, I want to get rid of, it bothers me, sorry. Okay, We expect it to be greater than the similarity between the encoding of the image with respect to the concept metallic, where metallic is really just text, or you can imagine, is the encoding of a prompt that just says, this is an image of a metallic object, or we can discuss how people encode that. And then we invented a simple specification language that would basically use greater than symbol to say that for an image X, 4 is greater than metallic. And then once we have these predicates, you can assemble them to write properties. So for instance, for an image X, if 4 is greater than metallic and 4 is greater than rectangular, perhaps we can say prediction is cat or prediction is dog. Or maybe vice versa, and this can be seen in some sense as a validation that the output of the neural network is given for the right reason. So if a network predicts it's a cat, we might want to check that for that image, concept fur is more prominent than metallic and fur is more prominent than rectangular. And if this doesn't happen, it's likely perhaps that the prediction is wrong. So you can imagine that you can use define and check these kind of properties. And in our original paper, we kind of try to use these properties to check them using decision procedures, but you can also imagine you can check them at runtime. And the assumption in this work is that verification is sound only with respect to the interpretation given by the VLM, which can be wrong, but the VLMs are trained on massive amounts of data. They are a rich repository of concepts. And the hope is that as these models are becoming better and better, then this kind of interpretation via VLM is becoming better. And then we can also use statistical analysis to validate this interpretation, and we can discuss more about that. And these are strong assumptions, but in our original work, as I said, they helped us make progress on the challenging problem of verification of these kind of semantic properties that go beyond, let's say, local robustness with non-bounded perturbations that people try to do for the image domain. So now where we are now, we have extended this kind of idea of using a VLM to analyze a separate perception module also for debugging. So this kind of technique can help you localize the layers where possibly something wrong can happen. Also, we use them as runtime monitors, for instance, to detect adversarial inputs and misclassifications. As I already explained, you can imagine that for our hypothesis was that for a misclassified input or an adversarial input, you can check at runtime the consistency properties with respect to basic concepts for the domain. And if they don't hold, then something is fishy about it. So this is kind of the idea there. And now I'm getting closer to Scenic, so very, very close. And temporal logic, we also have some results on using VLMs for temporal logic monitoring in the autonomous domain. So last year we had a student working on seeing if VLMs are good at estimating spatial relationships in a scene. And this is usually harder than just saying that a cat has fur or something like that. So, but he created also a data set and fine-tuned several state-of-the-art VLMs, and he was able to obtain, let's say, high accuracy VLMs that would allow us to encode properties, something like this. If there is a car within 25 meters of ego, then ego should brake. And this year, we had a student from the same group from University of Virginia, and I'll tell you a little bit more, where we are trying to move from analysis to generation. So you can also imagine, so we would like to use the constraints expressed with these concepts that are written in natural language and comes from requirements, for example, from the DMV manual or other safety documentation, and generate diverse sets of images that conform with the requirements. For instance, this would, we could express preconditions that would describe scenes in a constrained way, very similar to Scenic, but then we would like to use, let's say, large language models and generative AI to generate images that conform with those constraints. I hope I'm not, am I running out of time?
That's about it. We are at time, so maybe you could wrap up.
Yes, yes. So I wanted to give an example of the runtime monitor that, so we already have a runtime monitor that uses this kind of spatial information with VLMs and integrates with LTL for finite traces. And this can be used to analyze sequences of images or videos, either to retrieve videos that conform with some scenarios expressed as LTL properties, or to check maybe online some scenarios. So now, this is the last slide, sorry. So where do we see Scenic? So my understanding, and I have worked in the past, I had the privilege to work with Eddie and Sanjit. So Scenic is mainly integrated with simulators, but I wonder if we can connect it with Gen AI. So what is our understanding currently? So Scenic, okay, also defines constraints and is very sophisticated that describes scenes. And I can imagine we can use those constraints already to do constrained image generation. But ideally, we would also like to generate small videos that show a scenario described with Scenic. And there are several challenges. So I know Scenic has a way to define behaviors, which is very, connects very well with the simulator. But for Gen AI, I think there are different challenges. And I hope we'll discuss more, yeah, while we are here. So this is all. Thank you. Any questions, please?
So, very interesting idea. So you think Scenic can be used as some kind of grounding mechanism for generation, or I mean, one of the issues with typical generation is that they're not somewhat grounded. For example, if I want to generate images of a kitchen, then you may see something like a cat sitting over a kitchen, which is not what you expect. But
so this summer, actually, we got an understanding. We use again stable diffusion, which is actually linked with CLIP. And there are works that try to analyze the latent space for very careful concept editing. So we gained an understanding for that to do control generation of images with respect to constraints. So yeah, ideally, we would want, if we have an image of a kitchen, to check constraints expressed in natural language and also generate images using, for example, what I showed at the beginning, or to edit the latent spaces to impose the constraints on generation. So we have an understanding on that. But yeah, and I'm not sure about videos. We would need to talk more about it. But yeah, this would be the idea.
Okay, thanks again, Corina.
Thank you.
And thank you to everybody who volunteered to give talks today.